Hey, good morning, everyone, and welcome back to another class. Good morning, good afternoon, and good evening, just in case. Today, we switch gears again. Basically, today is the last day when I'm going to say something about ultra powers. So I first just wanted to wrap everything up and to say a few things that I haven't said until now. This is the last chance to do so. So as always, U and V are non-principal ultrafilters for natural numbers. And here are a few facts. First one, if A is a separable C-star algebra, and A is an elementary submodel of C, or technical term for this is that C is an elementary extension of A, and C has two properties. If it's countably saturated and its density character is Aleph1, then C is isomorphic to an ultra power of A. Not only that, but the isomorphism is commutes with the diagonal embedding of A. So this follows immediately from things that I said before. The reason why I'm saying it is that in some sense, this shows that ultra powers are inevitable, that they are what they are. So those two properties of the ultra powers, countable saturation and the density character being Aleph1, characterize ultra powers. Of course, here there is a hidden assumption, continuum hypothesis. If C like this exists at all, then you must have continuum hypothesis. But that's interesting, but not really directly mathematically relevant. Any consequence, any application of ultra powers to classification of separable whatevers, not only C-star algebras, in any application, use of continuum hypothesis can be removed. So it is more of a curiosity. The next thing I wanted to say is not directly connected to ultra powers, but indirectly very much connected to ultra powers and ultra products. Remember, a theory of C-star algebra A is just a functional, a character more precisely, on the Banach algebra of all sentences. I'm here saying sentences over the empty set. The sentences over the empty set. So you have this Banach algebra, all those sentences, and to every C-star algebra you associate a character on that algebra. Now, that set of characters is actually very nice. It is a weak star closed subset. Sorry, this is my alarm. So it is a weak star compact, and well, okay, it's compact Hollinger space. Now, the reason for why is it sigma closed? What did I just say? Sorry, I wanted to say weak star closed. I said sigma closed. We'll see sigma closed later on today. So why is it weak star closed? Well, if you have some theory, sorry, just a second. So if you have a net of theories of some algebras, A lambda, you don't really need a net. This is really a, yeah, why do I need a net? This is a compact metric space because our Banach algebra is separable. So it's a dual space is weak star separable. So I just say you have a sequence. You have sequence of theories converging to some character phi. You want to realize it. By it I mean phi. You want to realize phi as a theory of something. Well, you just take an ultra power limit as n approaches to u of theories of ANs is exactly going to be the theory of the ultra product of all the ANs. Right, so even if convergence was along ultra filter, which is not necessary here, you would get this, right? So this follows from Walsh's theorem, and also if you want separable C-star algebra, we saw that ultra powers are not separable, the proof applies to ultra products. If you want separability, just use Levenheim's column and get separable elementary submodel of this. Right, so all of these consistent theories form a weak star compact set. And now continuum implies also when two ultra products are isomorphic. Actually, this n approaches to U is not necessary here, so that they're isomorphic if and only if their theories converge along the ultra filter to the same character. Right, so for ultra products, theory is a complete isomorphism invariant. And one more thing.
Can I ask a question?
Go ahead.
So
Yes.
in point 2, you are regarding an infinite family of sentences or a single sentences to some extent.
No, I'm not. No, it's pointwise convergence. So it's weak star topology, right? So it's
yes,
topology.
But theory of A is given by a family of sentences.
Well, no, it is given. Well, okay, you can think of it as family of sentences, but the way I think about it is as a character, as evaluation functional. You see, if you think about it as a set of sentences, then there is no nice topology, really.
Okay.
But if you think about it as a character, right? So this is a character from the algebra of all sentences into real numbers, right? It's a real Banach algebra. Then you get a weak star topology.
Okay, fine.
So it's much more manageable. This is why I started by saying that really continuous model theory is to a large extent functional analysis. Really functional analytic methods are very relevant here. And they have been rediscovered in both subjects, many basic theorems. Every now and then you just run into something. Oh, I've seen this before in logic. Oh, I've seen this before there. Right. So any other questions? Okay. And the last, sorry, this is just, for some reason, my iPad is getting darker and darker. If you have countably saturated algebra C of density character F1, then you can write it as a union of an increasing chain of separable elementary submodels, right? So we used, if this is C, use Levenheim's column theorem over and over and over, and you obtain this continuous increasing chain of separable substructures. Now, by part 1, for example, C is isomorphic to ultra power of any one of them. And again, isomorphism is the identity on this diagonal copy of C alpha. Now, what is curious in case of cyst algebras here is that quite often you can choose all of these C alphas to be not isomorphic to each other. So basically you have this F1 increasing chain of cyst algebras that are all non-isomorphic, but their ultra powers are all isomorphic to a single algebra. This is not a trivial fact at all. It falls from quite a deep result of Marius Junge and Gilles Pissier. Basically, consequence of their result is that there is no universal separable cyst algebra. So if you give me any separable cyst algebra, there is a cyst algebra which is separable, which doesn't embed into it. From there, you can cook up example, but I would conjecture that this is true in almost any situation. I mean, if C is abelian, well, if C is specific abelian cyst algebra, this is not, you cannot get a chain like this. But I would guess that there are only few situations in which you cannot get all C alphas to be non-isomorphic. Okay. So that ends our treatment to ultra powers. I'm just going to mention them every now and then in various contexts. Actually, I'm going to mention them very soon, but just basically to lament that Kalkin algebra is not an ultra power, that it's not nearly as nicely behaved as the ultra powers. So we move on to my favorite mathematical structure, Kalkin algebra. Just in case you forgot, it is B of H modulo the compacts. and H is a separable Hilbert space. Now, just on this slide, it will be convenient to use a short notation for this quotient map. Remember, P is the quotient map from B of H to Q of H. I'll be writing A with a dot on top of it for the image of A, just to avoid having too many P's or Pi's on the same slide. So here is a theorem of Brown, Douglas, and Fillmore from the 70s. I'm not being precise here, not because I'm lazy. I mean, the paper was published in 77, but they've been working on this for a while, and it took a long time for a paper to appear. And really, their work was one of the most influential works in operator algebras, definitely in the 70s. And here I'm saying this is a BDF theorem, but it's not. This is a very, very, very special case of what they did, but it is the case that we are interested in right now. And here's what it says. If you have two normal operators in B of H, right? So remember, normal means that it commutes with its adjoints. Then you have these three equivalent statements. First, there is an automorphism of the Calkin algebra, which maps the image of A to the image of B. Note, this is important. A and B are in B of H, but I'm actually looking at what happens with them downstairs in the quotient. Two, there is a unitary in the Calkin algebra which conjugates A dot to B dot. And three, spectra of A dot and B dot are equal. Spectra as computed in the Calkin algebra. Now, this spectrum of A in the Calkin algebra, it is sometimes called the essential spectrum. It is essential spectrum of A itself, which has a natural definition. You can figure out what it is from these definitions here. Let me just say a few words about this. First, the fact that two normal operators are unitarily conjugate if and only if their spectra are equal fails miserably in B of H. Even for unitaries or for self-adjoints, the unitary equivalence of self-adjoints, for example, is known to be very complicated relation. By a result of Kekis and Sofronides, it is not classifiable by countable structures. So there is a turbulent orbit equivalence relation in Greg-Horst, in terms of Greg-Horst turbulence. However, equality of spectra is smooth relation because spectrum of any given operator is compact set of complex numbers. And compact subsets of a Polish space, such as complex numbers, form a Polish space themselves, right? So normally, when you pass to quotient, things become more complicated, and we'll see a lot of that in this course, definitely. But in this particular case, they become simpler, right? So after modding out by compacts, turbulent equivalence relation suddenly becomes smooth. Another thing is, of course, 1 implies 2 is trivial, right? No, it's not. Sorry, the other way around. 2 implies 1 is trivial, right? So if they're entirely equivalent, then there is automorphism which conjugates one to the other, and also 2 implies 3 is also trivial because conjugating by unitary doesn't change spectrum. So it's really going from 3 to 2, and also in particular going from 1 to 2 that are non-trivial directions. I just want to say one more thing more in direction of what BDF did. What all this tells us, well, you see, if A is normal, then the C-star algebra generated by A dot is just isomorphic to continuous functions on the spectrum of A dot. So really the way that BDF formulated their theorems, it was in terms of extensions of separable unital cyst algebras, such as these abelian cyst algebras. So this is just a special case of their theorem for singly generated abelian cyst algebras. Right, singly generated abelian means exactly normal operator, because that single generator is normal. There is much more there to say, but we are after this particular theorem. So you see, the assumption here is that A and B are normal in B of H. Okay. Now let's go back to Fredholm operators. So a few classes ago I mentioned them in passing, and I refused to say more about definition. But right now I'll be using it a lot, so I'll just say a few things. Operator is Fredholm if, I mean, this is not definition, but it's equivalence by Atkinson's theorem. I'll just write here. By Atkinson's theorem. A is Fredholm if and only if A dot is invertible in the Calkin algebra. Now, roughly, see, I'm referring to propositions from the appendix to my book. Of course, this is not, my book is not the right place to learn this, but you can find references there. And just for the sake of uniformity, I just keep referring to it. If A is Fredholm and if A and B have same image in the Calkin algebra, then B is also Fredholm. And also, if you look at dimension of kernel of A, by the way, note, if A dot is invertible, its kernel, invertible in the Calkin algebra, its kernel has to be a finite rank. It has to be a subspace of finite rank, and the same for its adjoint, because if A is invertible, then so is its adjoint. And this difference between those dimensions of their kernels, it is a natural, not natural, it is an integer, and it does not depend of the element of the equivalence class, modulo compacts. So this index is well defined for an operator in the Calkin algebra. And that is the Fredholm index. The difference, excuse me, the difference of those two numbers. Now, a few facts which are straightforward to check. Index of the adjoint is minus index of A, and index is multiplicative. It's basically linear algebra to check all this. So if you look at invertible operators in the Calkin algebra, and look at the map which sends A dot to index of A. Note, this is well defined, right? So I can choose A arbitrarily, but index doesn't depend on the way I choose it. This is actually a group homomorphism, and it is a continuous group homomorphism. Right? I'm taking norm topology in the domain. And moreover, that group homomorphism is invariant under conjugate. Oops, this should be U star. It is invariant under conjugation by unitaries in the Calkin algebra. I emphasize unitaries in the Calkin algebra because not all unitaries in the Calkin algebra lift to unitaries in B of H. Okay. And now back to BDF, sort of. An operator is essentially normal if after modding out by compacts, it happens to be, it looks normal. So somehow modding the compacts out normalizes it. I guess it's a bad terminology. Anyway, it becomes normal in Calkin algebra. And here is the important example of an essentially normal operator. Fix an orthonormal basis for H, Cn, and look at the unilateral shift S. So I just need to define it on the basis vectors. And S sends Cn to Cn plus 1. This is an isometry, right? So it basically just shifts your vector to the right by 1. Now, what can we say about that operator? Well, if you look at S star S, You just shift to the right, shift to the left, nothing happens. So it's identity. But S star, what is S star? S star is shift to the left. And now because my basis is indexed by natural numbers, I should have emphasized that. That's why it's unilateral shift. When you shift to the left, the first coordinate falls off the cliff. So when you shift back, you just have 0 there, right? So this the kernel of operator S star is this one-dimensional subspace. However, when you mod out the compacts, that one-dimensional subspace disappears and you get a unitary. And now, if you look at this unilateral shift, its Fredholm index is 0, -1, right? So it is -1, which means, in particular, that you cannot lift it to a normal operator. No matter how you lift it, what you get is going to be a Fredholm of index -1. And the normal operators, if they're Fredholm, they have index 0. Okay, so what it shows is that unilateral shift is essentially normal. That is what this says. Actually, just even this, right? So this says even more, but it's not normal. And not only that it's not normal, it is not even equal to a normal operator modulo the compacts, which means that BDF theorem does not apply to it. Okay, so we arrive at the question. Is there an automorphism of the Kalkin algebra which sends shift to its adjoint? Now, such automorphism, if it exists, it would be K-theory reversing automorphism of Q of H. You can ignore this if you're not sure what K0 and the K1 are. K0 of the Kalkin algebra is just 0. Actually, I shouldn't be putting, sorry. As a set theorist, I tend to put these Crowley braces where they're not necessary. So K0 is just trivial, and the K1 of Q of H is isomorphic to Z. And really the generator of K1 comes from the shift. So sending it to shift star would be an automorphism of the algebra which reverses K1. Okay, now you see from what I said so far, you can see that if you take any unitary, U S U star, I'm not saying the dots, I'm just saying US U star, but it's happening in the Kalkin algebra. This is never going to be equal to the adjoint because Fredholm indices of left-hand side, right-hand side different. So basically, what this is really asking, oh yes, and another thing is that the spectrum of S dot is the full circle. There are a few ways to prove this. One is by hand, just to check that S dot minus lambda is not invertible for any lambda. But another way is to just show, to first observe, since S is a unitary, its spectrum is definitely subset of the unit circle by continuous functional calculus, if you want. And now, if it were a proper subset, so if there was a point missing somewhere in the circle, then you would be able to find logarithm by continuous functional calculus again. Right? If you have a subset of the circle which is not the whole thing, then you can just continuously unravel it to the real line and find a self-adjoint element such that the exponential of I times that self-adjoint is your unitary. But if that were the case, then you can lift self-adjoint to a self-adjoint, and that would mean that you can lift the shift to something that has a logarithm, but you cannot because unitary with a logarithm is normal. Again, straightforward to check. So basically, out of those three conditions in a BDF theorem, one is true, okay, I didn't write, but from here it actually follows that spectrum of S star is also equal to T. So these two elements have the same essential spectrum. One item is false. You cannot conjugate one to the other by unitary. And what remains? Well, is there an automorphism which sends one to the other? All right, but now they realized that okay, so this may be a difficult question. Let's ask an easier question. Does Calkin algebra have an outer automorphism at all? Right, so definitely if the answer to this part is negative, then the answer to the first part is negative as well. So really the right way to think about, for me, the second question is as a test question for the first one, right? Is first one simply just pointless? All right, so this is the question that we'll spend quite a bit of time on from now on. Now let's try to see a model theoretic approach to a BDF question, right? So we just saw that in case of ultra powers, namely countably saturated algebras, we have very strong, powerful model theoretic methods that can construct isomorphisms and automorphisms of algebras. So to a logician, the first question to ask in a structure like this that has a reasonable model theory is, are the types of those two elements equal? Here I'm just looking at type over the empty set, right? This is what matters really. Well, we don't know much about this. So you see, from type you can compute the spectrum, but we know that spectra are the same. From the type you can also figure out what kinds of roots. Okay, you can see that it is a unitary also, but once you see that it is a unitary, from the type you can see whether it has square root or third root or whatnot, but neither of these two operators has any root, and that is because their Fredholm indices are -1. So if shift had a square root, Fredholm index would have to be -1/2, which makes no sense. And that is pretty much all that I know about their types. Alessandro Vignati computed certain portions of types of these operators, and they are equal. More precisely, he checked that universal types and I think AE types are equal, but computations get messier and messier each time you add quantifier, and we have no idea.
But suppose one could show that two types are equal, that wouldn't amount to a proof that you can send one to the other.
Exactly. Yes, that's coming up. Yes, thank you. Thank you for spoiling my punchline. Yes, right.
Oh, sorry.
It's okay. It was a lame joke. Here is another question, which is really, to me, I think this is really the crux of the matter. If A is Fredholm operator, can you recover index of that? Oops, this is a typo. From type of A dot in the Calkin algebra over the empty set. Right. You can recover absolute value of the index. That's what I was saying about square roots and whatnot roots. But can you really, question is, can you recover sign of the index? And I have no idea. Simply no idea. Right, but as Matteo pointed out, a negative answer would be conclusive, right? So if you have two elements with different types, well, then automorphism is never going to send one to the other because every automorphism is an elementary embedding. But I would say that negative answer is unlikely. And the argument is basically if there was a sentence distinguishing them, then BDF would have realized what it was. Of course, it could be that there is some sentence with 15 alternations of quantifiers, but I don't know of natural examples in which that happens. Now, as Matteo just said, since Q of H is not countably saturated, we cannot apply methods that we apply to construct automorphisms of ultra powers. Now, you may wonder why. Why is it not enough to just have a countably quantifier-free saturated? After all, automorphism is just needs to preserve quantifier-free types. But I would like to remind you of that example that we saw a couple of weeks ago, or a couple of classes ago, that you can have a map which is quantifier-free type preserving, namely, injective star homomorphism, that cannot be extended to automorphism, exactly because you don't pay attention to existential statements. So you can send a unitary which has a square root to unitary which does not have a square root, and then you're stuck because that square root has no place to go. And then you can say, well, but we just need to worry about existential statements. But basically, if you just worry about existential statements, then in the next step, you may run into some existential statement that you forgot to carry about. So, I mean, logicians know about so-called aerofoid phrase games. If you want to survive, with a back and forth finding automorphism up to n steps, your structures have to agree up to n levels of quantifiers, up to n quantifier depth in those structures. And it is actually amazing that if they completely agree with all quantifiers, that you can survive even past countable transfinite stages. That the whole process goes on transfinitely. Okay, one more short intermission. Right, so this is what I said before. Here is an exercise. If you take a unitary in the Calkin algebra, then prove that either U has a logarithm, so either it's exponential of IA for some self-adjoint and even self-adjoint of minimal possible norm, or there is an n, so that U has an nth root if and only if n divides n for all n greater or equal to 2. And so there is a strong dichotomy for unitaries in the Calkin algebra. Now here is rather unfortunate but well-established terminology. Supernatural number is a formal product over all primes of powers of those primes. Powers go from 0 to infinity. By infinity, we mean Aleph 0, countably many. So for every such formal product, there is a unitary in, this is a unitary group of ultra power of the Calkin algebra, which has the property that it has nth root if and only if n divides that supernatural number. So you can, for example, produce a unitary which has 2 to nth root for any n, but it doesn't have a third root. And there is no such thing in Calkin algebra, but in the ultra power you have it. Okay. So let's go back to Calkin algebra. Just one more intermission. I just have to mention one of my favorite theorems ever. I'm not going to state it, but set theorists know it. There is a beautiful theorem of Hugh Woodin, which is more general than what I'm going to say. But basically, if in some model of ZFC there is an auto-automorphism of Calkin algebra, then there is an auto-automorphism in every model of ZFC constructed in a reasonable way that satisfies continuum hypothesis. And analogous statement holds for K-theory reversing automorphisms. So in case you're not sure, this is a sigma 2-1 absolutist theorem. So all that, the only reason why I'm saying this is that to a set theorist, it is immediately obvious that if you want to construct an automorphism of Calkin algebra, you might as well assume continuum hypothesis and see what happens there. And then see if you can remove it. And Phillips and Weaver indeed proved that continuum hypothesis implies that the Calkin algebra has 2 to Aleph 1 automorphisms, which is really the maximal number. I mean, it has 2 to Aleph 1 endomorphisms. Now, in some sense, all proofs of this sort are similar. It resembles construction of 2 to aleph 1 automorphisms of an ultra power, but there are two differences. So let me just first say what are similarities. So you just write calc in algebra as inductive limit of separable subalgebras. No worry about elementary submodels here. And then you construct for each one of those an isomorphism with, so this is another copy of calc in algebra here. And then you go back and forth and then try to survive until the end and construct an automorphism of the entire thing. Right? We saw before that automorphism has to be constructed that way, that always you're going to have a closed unbounded set isomorphisms between, even automorphisms of separable subalgebras. However, you see, because this is not obtained by realizing types, one needs a different device to make it survive through the limit stages. So their device is actually assuring that each of those partial isomorphisms between separable subalgebras is implemented by a unitary. Basically, it is a restriction of an inner automorphism to a separable subalgebra. Now, that makes it much easier to survive in successor stage. You have a unitary, it works on a separable subalgebra. All that you need to do is find two distinct unitaries which conjugate your automorphism which implement the same automorphism of separable subalgebra, but somehow disagree. Corresponding automorphisms disagree on some other element. And for that, you just need to know that in the relative commutant of your C algebra, there exists a non-trivial unitary. Once you have that, you can just multiply unitary with it and go. So the successor stage is very easy, but the limit stages, which are trivial in my case, well, my case, I mean, model theory case, are actually horribly difficult here. You see, because you have sequence of unitaries, you have this increasing sequence of algebras, and that sequence is, okay, they agree on your chain, but in the limit, it's very difficult to control what's going on. You need to find a unitary which is going to implement exactly the same automorphism in the limit. So indeed, if you work with a sequence of unitaries, you would be dead almost certainly. What Phillips and Weaver did, they actually made sure that they have a continuous path of unitaries. So we are talking about asymptotically inner as opposed to approximately inner, which is a big difference. And yeah, so at the limit stages, they use a very intricate homotopy argument to find this implemented unitary. And quite a few of the ideas come from KK theoretic arguments. So to me, this was one of the most difficult constructions using continuum hypothesis I've ever seen. But this is not what I'll be doing. I'll be presenting a simple proof. But oh yes, right. So this is sort of very off tangent, but I just wanted to say something. It is somewhat illustrative in what happens with homotopy here. Because this is really about homotopy to a large extent. If you look at unital copies of n by n matrices in the calc in algebra, they're all unitarily equivalent. That's easy exercise. However, there are n homotopy classes of such unital copies. Right, so you can have unitarily equivalent but not homotopic copies. Yeah. Okay, this has to do with the Fredholm index, as you might guess. Okay, so as I said, plan is to present what to me is simpler proof of the Phillips-Weaver theorem. I believe that actually Phillips, I think he wouldn't agree definitely with this. I mean, you know, somebody, I think it was Thurston once said that triviality is in the eye of the beholder. You know, what you know is more likely to be trivial to you than what you are just learning. So this is simpler proof to a set theorist to somebody who is an expert in KK theory, Philip's Euler proof is probably more natural. But really, the ideas are very elementary. So let's go. Let's go with a warm-up. So sigma directed posets. So poset is just a partially ordered set. And here is a lemma. So if you have a directed poset, I remember directed means, oh, it's directed upwards. So it will be important. Directed is always going to mean directed upwards here. So it just means that if you give me any two elements in P, there is a third one, which is bigger than both of them. If you have a directed poset, if you partition it into finitely many pieces, then at least one of those pieces is cofinal. And the proof is easy. So if I write P as union J less or equal than N xj, so assume that none of these xj's is cofinal, and then fix aj in P such that for every x in xj, aj is not below x. So here I have a1, a2, to an, but my poset is directed, right? So there is a single element above a1 and an, and by induction, there is a single element b, which dominates all of these a's, but where is b? This was supposed to be a partition, right? So this b has to belong to some xj, but aj is below b, and aj had, oh, this was xj, and aj was supposed to have this property that no element of xj dominated it. Right, so this is a straightforward fact from combinatorics. What I really need is a variation of this fact. Just a definition here. A partial ordering is sigma directed, or sometimes, especially model theories, you can see them calling this Aleph1 directed, if every countable subset is bounded above. Now, there is a big warning sign here. This is not the same as saying that every countable subset has a supremum. This is strictly weaker. For example, in a countably saturated partial ordering, no countable subset is going to have a supremum. I mean, countably infinite subset, because by countable saturation, you'll always be able to squeeze something between those countably many elements and below that element. So this is weaker. And we'll see a very natural and important for us sigma-directed partial ordering. So here is lemma. If a sigma-directed poset is partitioned into countably many pieces, then at least one of them is cofinal. Proof is identical to the proof of the other lemma. Right? You just partition it, assume the contrary, choose one element which is not dominated by anything in the jth piece, you get a countable set. That countable set is dominated by something. That something better belong to one of those countable many pieces. End of the story contradiction. Before I turn the page, just one explanation. You may be annoyed that, I mean, if you look at the numbers of lemmas that I'm covering, I'm going all around the book. Basically, the reason is that I want to present something. There is much more information that is used in other places related to this, both in chapter 8 and in chapter 9. But this is really all that we need from those chapters. So I'm just basically going for automorphisms of the Calkin algebra. I just had to make a choice of what to cover in one semester course out of 500 pages. Okay, so back to the Calkin algebra. Right, this is also in chapter 9, sorry. So I'll need this from chapter 9. So here is the poset part sub n. To a set theorist, this resembles various posets that are very popular in set theory. If one of them is functions from n to n with eventual dominance ordering. You don't need to know what this is. This is really a variation of that. But I don't think this was considered before, but this is exactly what we need for Calculus algebra. Okay, so here is the definition. So part sub n is set of all partitions of a cofinal subset of n into finite intervals. In other words, this is my natural numbers. So 0 is here somewhere. So I just choose a sequence of numbers, n of 0, n of 1, n of 2, and so on. But my object that I want to record is not this sequence. Instead, it is this partition into these, okay, I'm writing them as half open intervals. Of course, this is discrete set, so half open doesn't make sense, but I just want to make them disjoint. Right, so it's repartitioned in these intervals. And you see, it is important for some technical reason, which is nothing to worry about really, that I'm not partitioning all of n, but just cofinal subset. So here I just allow just basically forgetting about some finite subset of natural numbers. It's not going to make any difference. Okay, and the notation is E. So E is this sequence of EJs, and EJ is this jth interval from nj to nj plus 1, right? So this is E0, this is E1.
By cofinite, you mean cofinite?
Oh, cofinite, thank you.
Cofinite would mean infinite.
Yes, that would mean something very different. Yes, thank you so much, cofinite. Yeah, thank you. Thank you. Yeah. Right, thank you. Actually, Piotr also texted me. Yes, thank you. Thank you both. That's what I meant. Okay. Any other questions or remarks? Okay. Okay. So here are three definitions. So basically, on this set, we want to define partial ordering, and here are three candidates. Let's take a look. First one says that E is less or equal star than F if for all but finitely many m, there exists n such that En is subset of Fm. Right. So when looking at that ordering, I'm starting from F and then looking at these intervals F0, F1, F2, and so on. So they're so big that eventually each one of these Fms is going to contain at least one E. So let's say that these are E's. Here is E0. Here is E1, E2, E3, E4, it jumps over, and so on. So you see, in this case, at least from what we can see in this picture, everything is fine because we have that E2 is subset of F2, right? It's completely included, contained inside F2, and E4 is included in F3, and so on, right? So this is what the first definition requires. The second definition is something that may seem very similar, only quantifiers are switched. So here, it is E that is primary. So it's E0 is here, E1 is here, E2 is here, E3 is here. So now, in order for F2 to be bigger, I need to have that for all but finitely many n's, there exists an M so that En is subset of Fm. But now look at what that forces me to happen. So let's say, okay, so we can have some garbage going on here. But eventually, let's say from E1 on, if you want this to start happening, well, it means that this, oops. You see, if I have Fn here, this is already forbidden, right? Because E2 will not be included in any Fm. So I'll try to backtrack here. So what is really necessary is that any later Fn either is equal to En, or it is equal to union of finitely many of Ens. Right, so if any Fn ends in the middle of one of the intervals En, you will not have the ordering. So actually, the second ordering is a bit messier, a bit more stringent than the first ordering. And now the third ordering, the definition, at least superfluously, looks different from the other ones. So quantifiers again go from E to F. Again, we look at E as the primary ordering. Let me just draw it again: E0, E1, E2, E3, and so on. Now, what is required now, that for all but finitely many I, oh, by the way, I just assume that everybody knows this quantifier, right? So logicians know it. Right, for all but finitely many means, well, for all but finitely many, right? So you can have injury finitely many times, but from some point on, this body of the statement is true, right? So for all but finitely many I, there exists a J, so that EI union EI plus 1 is subset of Fj union Fj plus 1. Right? So now, you see, this is really different from the other one, but let's leave it for the moment and move on to discuss the first two. I'll just leave it to you to think about it, but we'll come back to it in a moment. So here is the lemma. First, this poset this first poset here, it is sigma directed. So for any countable subset of part n, there is a single element which dominates all of them. So let's the proof. So fix E of n for n in n. I'm writing E of n because I'm using subscript for these intervals. Okay, so I want to find Fn, which will satisfy this F, sorry. I want to find F, which will satisfy this requirement here. So for all but finitely many M, there is an N such that this happens. So we can just let F0 be E0, 0, right? The first interval of the first one. And now, let's see, it's E0, 0, E0, 1. Okay, so actually, maybe it's easier if I just write this. So here is E0. Here is E1. Now, probably, we are looking at the worst case scenario. E1 is probably a bit sparser partition. E2 is even sparser, right? So making it more difficult for us to find these. So I just said let F0 be E0, 0. So it's this one here. Now, what do I want for F1? Well, I want to make sure that I choose F1 so that F1 includes E0K and F1 includes E1L for some K and L. Right? But this is easy. So I just basically look at the next one here and just look at E1 is a partition into finite intervals. So only finitely many of these intervals hit what I have so far. So I can just choose the next one. So it is. So this is my E1 L, and here is my E0K. So I just choose such finite sets and just take F to be big enough to contain all of them, right? And in the end stage, so if F0 up to Fn have been chosen. Now, of course, it is the inductive requirements are that maximum of Fj plus 1 is equal to minimum of Fj plus 1, and that Fj includes, okay, so for every, sorry, for every L less or equal than J, there exists some K such that Fj includes EL sub K. Right. So at every stage, I have just finitely many intervals to include. Right. So if I have chosen this, well, just see where I am, and I can just choose as long finite interval as I want, and I can cover as many other finite intervals as I want by it. I just have finitely many of them to cover. So this produces F. Okay. Any questions? Okay, so now the next lemma is that these two orders are actually the same. I mean, they're really equivalent. The definitions of these two orders are equivalent. So let's take a look at that. I think, no, I'm here. So first, suppose that E is less or equal star than F. Right, so there is a definition. I need to prove that E is also dominated by F in this other ordering. Okay, so fix M such that there exists N such that En is subset of Fn. By our assumption, this is going to happen for all but finitely many of the M's. Now, let's take a look at this situation. I'll try to keep Fm green and En's red. Now, because En is subset of Fm, so it needs slightly stronger assumption, such fix M such that for every M prime greater or equal than M, this happens. So I'll need it for the next N as well. So here I have En. Now look at En. Oh, let me see. I think I should do something about my battery. Just a second. So here is En. How far can En plus 1 go? Well, what I want to prove is that En union En plus 1 is subset of Fm union Fm plus 1. What if not? Well, that would mean that Fm plus 1 ends before En plus 1. So, right. So if En union En plus 1 is not subset of Fm union Fm plus 1, then this would mean that En plus 1 is not subset of Fm plus 1, right? Because remember, En was subset of Fm. That meant that the minimum of En plus 1 was less or equal than the minimum of Fm plus 1. But also, actually, what we have is even worse than that. En plus 1 includes Fm plus 1. So there is nothing that can be a subset, right? So Ek is not subset of Fm plus 1 for all k, right? But our assumption was that n was big enough so that for all n prime from that point on, there is always one of the en's subset of Fn, right? So we proved that E less or equal star F implies E is this double less or equal star than F. Now assume the other way around. So assume that T is double less or equal star F. So let me just write down what this means because it disappears from the screen. So it means that for all but finitely many I, there exists J. Yep. Apologies for the handwriting. Such that EI union EI plus 1 is subset of Fj union Fj plus 1. Okay, so again, just like a moment ago, fix I. Let's sorry. Okay, you know what I mean. So fix I large enough, right? Large enough so that this holds. And now we want to check that E is less or equal star F. All right. So let's take E was red. I'm trying to be consistent here. So here we have EI. Here we have EI plus 1. And now take any Fn that starts late enough. Now, what is late enough? Well, I just want minimum of Fn to be greater or equal than minimum of EI. Well, let's see, can this happen? So this is basically the bad case, right? So this is a situation in which Fn does not have a subset. Maybe it's not, I mean, you could argue, well, maybe Fn starts much later here, but then I just have two different indices. It's some even larger I. So assume that Em is not subset of Fn for all n. Okay, so let's enjoy it again. Sorry, my iPad sometimes is moody when I'm trying to scroll the screen. So here is Fn. Now, what does it mean that Em is not subset of Fn for anything? Well, it means that whatever is this one here, so what is EI? There is a unique EI whose maximum, EI, okay, so sorry. So fix minimal I such that EI intersected with Fn is non-empty. Right, so look at that if EI. Well, our assumption is that it is not subset of Fn, so it starts earlier. Right. So then EI is not subset of Fn. Okay, but now what about EI plus 1? Well, by our assumption, EI plus 1 is not subset of Fn either. So EI plus 1 goes somewhere like this. And also EI plus 1 is not subset of Fn. Okay, so what this means is that if I take EI union EI plus 1, it is not subset of Fn union Fn plus 1, right? It sticks to this side, but it also sticks to this side. It's also not subset of Fn minus 1 union Fn. And these are only two possibilities because they both hit Fn, right? So this condition here is violated. Right, so EI and EI plus 1 is not subset of Fj, Fj plus 1 for all j. Okay, so you may be wondering what this has to do with Calkin algebra, but just bear with me. Okay, any questions? Oops, let me write here. Okay. All right, so we just finished the second part of the lemma. Oh yes, and the third part is that this poset that looked very similar to less or equal star is not even directed. So just forget it. So it's not, you'll not need it. All right, now we want to connect. What? My slides seem to be going backwards, or well, this is the same slide. Okay. Okay, so now we go back to operator algebras. I haven't defined what is von Neumann algebra. I told you that I'm not going to need them and that is true. But just the C-star algebras that I'm going to need next happen to be von Neumann algebras, which is totally relevant for what we are doing. But it would be a shame not to say so. So I'll just say so, but it's really not being used in the proof. And I'll say what this means exactly when we come to that. So again, we have H with a fixed orthogonal basis Cn, and now we have this E in this posted part N, and fixed subset of natural numbers. And look at this projection. So let's read the formula from the very inner part. I take union of all ENs for n in X. And then take all the CIs, right? CIs are these bases. Take the span of all those CIs that lie in any of those intervals. Right. So I first partitioned my space by my, well, really think of ENs as partitions of bases into finite intervals. And you take a span, closed linear span of everything that lies in this union indexed by X. And look at that projection. So that's what I denote PEX. And now look at the following. D of E is all operators A such that for every M and for every N, if XCM inner product with Cn is non-zero, then M and N belong to the same interval. Now, one way to visualize this is just as big matrices. So just think of elements of B of H as giant matrices with respect to this basic Cn. So what is bounded linear operator? Well, in particular, if you just look at every row of that operator, it is coordinates of some vector which is of norm at most 1, say, if you're talking about operator of norm 1. Right, so all the rows are in L2, and also all the columns are in L2, but what we really want is to look at this. Now, for this picture, I'll look at E as partition of the entire set of natural numbers, not just the cofinal set. It's just going to be easier to draw. So here is interval E0, here is E1, E2, and okay, so on. Now, and also in the vertical direction, I have E0 and E1 and so on. Now, look at this block matrix. So what this is saying is that all the non-zero coordinates of A are in one of these blocks. Right, so if Xn is not 0, then M and N belong to the same block, meaning that A is outside of all of this is 0. So these are just block matrices. Now, D of E is closed under addition and multiplication and adjoint. It's also norm closed, but here is the phenomenal algebra part. You see this condition here, it means that if you think about these operators as functions from H to H, just continuous functions from H to H in pointwise topology, even then it is closed, which pretty much means that it is a phenomenal algebra, right? So it has even stronger closure property than just being norm closed. And here is this other algebra A of E. So here it is. Just look at all of these projections. So it's PE singleton N, right? So if X is just singleton N, I'm just looking at this finite dimensional space, only those CIs whose index I is in EN, taking projection with finite dimensional space, and now I'm just putting different coordinates to this. So this is just basically copy of L infinity. I'm taking L in lambda n, scalars in L infinity, but just putting them on these orthogonal finite rank projections. In other words, I mean, if you're familiar with phenomenal algebras, this is just a W star algebra generated by all these projections, PEX. All right. So lemma is that D of E is a von Neumann algebra. So it's closed in weak operator topology. It is what I said. Well, okay, it's not what I said. Sorry, but that's what I said was strong operator topology. So I'll just it's equivalent. So I'll just change S to W and it's equivalent. I just used the theorem of von Neumann, but that's okay. Self-adjoint sub-adjoint B of H and A of E is its center. Okay, so I maybe just made this complicated by invoking von Neumann algebras, but really this is really a very simple fact. Basically, D of E is nothing but the product of matrix algebras. Right? Remember that picture. The operators in D of E were those block matrices, and each of these blocks was just K of M by K of N matrices, where K of N is cardinality of the nth interval, E of N. And what is A of E? Well, in each one of those blocks, you're just looking at scalars, right? This is lambda n. So it is the center of this. And right, so this is algebra that we saw before, right? If you want, it's the multiplier algebra of the direct sum of these matrix algebras. Okay, now these are sub-algebras of B of H, not of the Calkin algebra, but of course, you'll be modding out by compacts in no time. Any questions? Okay, now before we go on with what we have to do, just note that the unilateral shift, it does not belong to any D of E, and even when you mod out by those compacts which are in D of E, this image of the shift does not belong there. Now, before I sketch a proof of this fact, the idea here is that if your partition gets coarser and coarser, you get more and more operators in D of E, and hopefully you get everything that you need. Well, but even this simple operator is not there no matter what. For this, to prove this, I'll just draw a picture. So what does D of E look like? And so no matter how you choose these intervals, it looks like this. Now, what does the shift look like? Well, it is, let's see. So it sends C0 to C1, which means that I'm probably going to get this wrong, but the shift has matrix that is diagonal, but it is diagonal, it has ones just below the main diagonal. Right, so it has zeros on the main diagonal and ones just below the main diagonal, which means that each time one of the EIs stops and next EI starts, you have this one here. Or in other words, if you prefer doing this in symbols, so fix some E in part, then for every n, if you look at shift times projection, so I'll use this notation, xn, this operator, I just want to make a little bit more room. And the next one, this operator here is norm 1. And that is exactly this one here. Right. So even after you mod out by compacts, the shift is not going to be there because it doesn't. Okay, so shift. Well, I guess I proved it, right? Yeah. So if A belongs to D of E, then if I look at A dot minus S dot, the norm of this is actually equal to 1 because of these ones here. So pxn plus 1 A pxn is equal to 0 for every n. Okay, so the shift is not there. So what are we doing? Let's take a look. Oh, yes, here is the picture of what is going on. So what we want to do is for any E in part n, define two coarser partitions, E even and E odd. Just for definiteness, I take E minus 1 to be the empty set. So E even, the nth interval of E even is E to n union E to n plus 1. And for E n odd, it's E to n minus 1 union E to n. So you can see here what it looks like. So what you see in this picture is the algebras D of E even and D of E odd. D of E odd is the one with the solid lines, and d of e even is 1 in the broken lines. So the operators which are inside these block operators. Now, problem is that the union of these two is not an algebra, but that is not going to be a problem. So really, just the plan, what we want to do is look at those operators whose matrices are included in an area that looks like this, so that we can find some fast enough partition so that graph of our operator, not graph, but the matrix of our operator can be covered by something that looks like this, and we have zeros on the outside, and then we'll go from there. It's slightly slower than I planned, but okay. And part of it is that my iPad is refusing to scroll. Okay, so here is the key lemma. Let's just prove that lemma and then we can stop. So if we have a Hilbert space H with orthonormal basis Cn, and if we take any sequence of operators in B of H, then we can find E in part of N, which is fast enough. By fast enough, I mean high enough in that less or equal star ordering. And now for each of the ANs, we can find AN0, which is in D of E even, and AN1 in D of E odd, which has the property that AN is modulo the compacts equal to the sum of the other two. Okay, so sorry about it.
But,
yes.
But why are you indexing your lemma with the natural numbers? So wouldn't it be okay just to have for a given operator you can find the coarse partition?
That's correct. That's correct. Yes. Yes. Of course. Of course. So exactly. So because so Matteo just made an excellent point. It's enough to find for each operator for single operator one partition, because then if you give me countably many operators, that lemma gives me countably many partitions, but the poset is countably directed, so I can find a single partition which does everything. Sure, yes, you can, but really doesn't make much difference, really. But you're right. So basically, this is lemma that I stated is a corollary to the light. Sure. So actually, that's what I'm going to do. It is slightly easier. So just fix single A and B of H. And now what is the point? Well, so we can really start with E0 arbitrary. So oh yeah, actually. So we'll find N0 less than N1 less than, and so on. So I'll find my partition but by finding this sequence of natural numbers. I'm sorry, I have no idea. Sometimes iPad just starts, giving me hard time scrolling. Like, no idea. Okay. So just fix N0. We can just take it to be 1 or whatever, and even N1 to be 2, just to get started. Now look at. Oh yes, so I'll be using this notation even with partially defined E. So Ej will be the interval from n of j to n of j plus 1. Even I'll be using this notation even when not all of them have been defined. Now, what do we have? This projection PE0, this is a compact projection. So if I take this is compact operator. It's actually rank 1 operator. So, and also the other way around, P is 0A is also compact. Right, so find N2 so that okay, I need another bit of notation. So let's say that RK is projection to the closed span of Cj for j less or equal than k, actually less than k for consistency. So clearly there is some redundancy of notation between RKs and PEXs, but it will be convenient to have RKs before we define all the NJs. Note that RK is an approximate unit for the compacts. You can guess my iPad is refusing to scroll. Okay. So what do I want? So find N2 so that Rn2 times we want to look at these compact operators. A P is 0 minus AP is 0. This has norm less than 2 to minus 2. And also Rn2 times P is 0A minus P is 0A also has norm less than 2 to minus 2. Right? So I can do this. And next, let me just draw a picture here. So basically, what my operator A looks like. No, actually, sorry about this. You know what? Maybe I'm rushing this too much. It's 427. So basically, essentially proof continues like this. You just choose these NIs, higher and higher. The entire idea is that, as I said before, all the rows of our operator A are in L2. So if you just go high enough, what remains is residual. So you can pick a fast enough sequence. But I'll just prove this lemma properly next time. It's important. So there is no point in rushing it right now. So I'll just say next time. Or if everybody reads the proof and just let me know. No, actually, no, I'll do it next time. So, okay, I'm sort of finishing this. Yes?
You can make the remaining stuff Hilbert-Schmidt, I guess, right?
That's correct. You can make it Hilbert-Schmidt. Yes, I just don't need it, but you can. Yes, absolutely. Yeah. Yeah, no, this lemma has been rediscovered several times. George Eliot has some version of this, and something like this is true in multiple algebras. So there, it is useful, but I mean, I don't have in particular application for Hilbert-Schmidt version, but yeah. Oh, actually, I think Voiculescu had some nice applications for that. Yes, that's right. Yeah, so maybe it's more useful if I just say where are we heading. Basically what I want here is to somehow define my automorphism of Kalkin algebra not on separable subalgebras, but instead on these subspaces of operators that can be covered by DE even and DE odd in some way, as in this lemma here, and that will suffice. And the fact that both it is sigma directed is going to be very instrumental in finding automorphism, in implementing this automorphism. Okay, yeah, so it's 4:30, so I guess it's probably time to stop. Yeah, I'll continue next time. So obviously some of you don't need to hear proof of this, but I'll just, for completeness, I'll cover it next time, and then we'll move on to see how to construct an automorphism using continuum hypothesis. Any questions? Let's scroll back to the proof of the equivalence of the two. Yes. Okay. So I mean, it's probably better if I just show you a place in the book. By the way, as I said several times before, if in case you don't have, okay. So here is the proof. You can tell me which particular part of the proof you'd like to see, so I can just start. So in case you don't have a PDF out of the book, just let me know. I'll be happy to share it. So am I at the right place in the file?
Down a little bit.
Down, okay.
So you're supposed to show something for cofinitely many n's, right?
Yes. M must, yes.
Is it n or m?
M. Right, because let's see. So what am I showing? No, n's, you're right. N as in Nicholas, yes. Okay, I see your point. So I wasn't clear about that point. So basically, yes, good point. So what I'm showing is that for each En that starts after at or after Fm, this is correct. Right. So for every n, such that minimum of En is greater or equal than minimum of Fm, we have that there exists whatever I call it, J, such that En union En plus 1 is subset of Fj union Fj plus 1. So this is what I'm showing. Yeah, thanks. So I was I guess slightly sloppy about that part.